good afternoon. Today we're going to talk about some different things. We'll do an introduction as well. All right, a couple upcoming things. Once again, please, we should have a notebook out and a calculator. Right, Hunter? A notebook out and a calculator. Everybody else has it. But I'm glad you agreed with me, because that makes me feel like you're with me. And even Ryan has it.
What does that mean?
I'm saying, like, be more like Ryan.
Oh, okay. We're talking cheese. Oh! Throwing dabs up there. You got to teach Mr. Coonan how to do that.
So, your lab's due today. It is such a shame for you to have a performance on the lab of an 8.
That's yours.
That's Mr. Anderson. An 8, a 9, a 10, and then you hand it in late. It's like getting a 5 or a 4 or a 3 automatically on that part. Secondly, it's also a shame to have a score for your lab and then not do the post-lab questions. Okay, the performance part is the part that would be, to be honest, the hardest part to achieve. So you had a group, you could have done the calculations with them right away. You were doing it all together. So if you didn't maximize that time, I'm sorry. Tomorrow we're going to review, and then because of the lip dub, we have a quiz instead of a test. Because we only have 35 minutes instead of 55 minutes. So we are going to have a quiz. We've geared back. We've taken a lot out of the test, and there's a little bit of each thing that you'll be required to know. And I'll show that to you at the ending of the period today. Gas is 5. You're going to get that today. That's going to be due on Friday. If you didn't know, I'm sure you do. No school on Monday. And then I know we don't have class on Tuesday, but we are going to get an introduction today of what our fire suppression systems are. And I will tell you now, the sooner certain groups get going, the stronger that's going to be, the better it's going to be. It is a huge grade. It's basically 2 big labs. It's worth 50 points, lab points. It basically sets the tone for the rest of your fourth quarter. Every year I've done it. If groups spend the time and work together and try to pump out a quality product, they do very well. It's not like technicalities get them here or there. They might lose a point here or there, but usually they do very well on this. The ones that wait until the last minute or don't seem to think that getting it all in is a big deal, then that is usually a disaster. So hopefully we're going to be on the right side of that. Okay, so today in our notebooks we're just going to do a couple examples, please. I hope we've already seen this and we don't have to write that down at all. That should look really familiar to us. If it doesn't, we've been doing it for months, this flow chart. So I want to review a little bit of how some of this works first. So if you would like to, you don't have to write it all down. You could just organize your information instead of writing the whole words. But we're going to do about 3 total problems today, maybe 4. We're just putting them right in a notebook. So if you want to just call this gas review or whatever. But instead of maybe writing it all out, learn how to paraphrase. I want grams of water when I combust 10 liters of propane at STP. Okay? So I want to talk about what that means. We're going to calculate this. We're going to see how we do this. This would be expected of you on the quiz on Friday. So I want to just discuss this. You should have kind of learned about this last week in different ways through worksheet that we had a little bit and then also through some lecture. So I want grams of water from liters of propane. So I'm starting with liters of propane. I want grams of my water. And here's the equation. I mean, at the minimum, if you're like, I don't want to write all that down, I'd write the equation down. And what we're going to do is we're going to organize. So what I have is I have 10 liters of propane, and I want grams of water. Okay? So I guess my question to you, and you're going to help me out with this a lot today. Can I do 3 steps? Is this okay? Can I go through each of these steps? Can I just do T-charts? I guess specifically, can I do this one right here? Is this okay? Can I go through that? Yeah. I can because I'm at STP. And regardless of what you're going to write down, make sure that you do stress STP. So if you just wrote this down, you got to say at STP. So minimum, just so you're understanding this, because you're not going to have a ton of stuff to potentially look over if you don't have the examples written correctly. We're at STP. So I'm looking at a 3-step T-chart, right? So this is what I've done for you. I'm filling in some of it. You're going to fill in the numbers for me. So every time I go to something, that should be on the top. Whatever I'm coming from goes on the bottom, and so on and so forth. Okay, so that's the beginning of it. I'm going to ask random people what the numbers are. There's 6 of them. What all goes in there? So you try to fill the whole thing in. You're like, I can't do this. Well, this is why we're practicing this again, but it's all in the context that we've been doing. So I'm going to give you a minute or two to do this. But again, the first one is going from liters to moles. This is my mole ratio, and then this is my moles to my grams, right? That's my 3 steps. So I'd like to know what the final answer is. I'm going to ask for numbers. If you know units, numbers just fall into place. Proven fact is that's pressure. Ryan, you get 6 options. Tell me one number anywhere.
Oh. One on the top mole. Yeah, right there. Yeah.
I will agree. Francis, you got 5 more choices.
22.4 is on the bottom of one.
Nice. So just a quick talk about that. Anything that's touching the moles within either side is 1 mole of that, and then it's either 22.4, it's 6.022 times 10 to the 23rd, or it's what it weighs, okay? That's how that usually works, okay? And it does matter. But Lane, give me another one. Anywhere. You got 4 of them yet. 18 right here. Awesome. Well, how do you get that? 1 plus 1 plus 16, right? 1 plus 1 plus 16. Sarah, give me another one.
4 mole on the top.
Where did you get that from?
In the equation for H2O.
Right there, right? Mole ratio is always from the equation. That's very important. Tessa, you only got 2 left.
1 mole of H2O.
All right. And the last one. Who wants that? Savannah, what do you got?
1 mole
Where'd you get that from? From the equation, because there's 1, right? So, if we can do this, then great. Right? It's going to be just like this. We might pick this exact one. Who knows? Weirder things have happened, I'll tell you that. And that would be my answer. So if you got the answer, awesome. 32.1 grams water. Okay. I'm not meaning for you to rewrite all this out. So just understand this when we go to the next problem here. So that's if we're at STP. I can flow through all this. If I started with grams and I ended with volume, I can still go through that if I'm at STP. What is STP? If you do not know, you might want to just write it down right here. Pressure is at what? 1 ATM. There's many variable or units that I could go with that, but we learned that it's 1 ATM, it's 101.3 kPa, it's 760 torr millimeters mercury. Those are all the same things. What's the temperature? 273 or 0. 273 is better, but if you could just remember 0 and 1. 0 and 1. That's it. That's STP. So, what happens when you run into a problem like this? All right. So, personally, you don't need to rewrite it all. A lot of it's the same. I'm still asking, I have 10 liters of propane, I want to know grams of water. I'm still asking the exact same thing. I have 10 liters of propane, I want grams of water. Here's the difference. I'm at 735 torr and 21 degrees, not STP. So, how does that work? Well, what can't I do? I can't go on that path, or if I was ending to volume, I can't go on that path. So what we learned is that we have to take a detour. We have to get onto this, but we can't go through this path. So we have to jump it. If you're like, well, how'd you know it was N equals PV over RT? Because N equals moles. So I have V, and then P and T are right here, P and T. What if I needed to end up here? Well, I need to end up with V, so I would have had to jump it. This is N, and then I'd have to be given T and P. So this is my path. I'm going to take the purple path, and then how many how many steps in my T chart? What do you guys think? So I go here. I need to get to grams. How many more steps on a T chart then? 1, 2. Okay. So let's start that off. So again, if you're like, well, I don't know what to write, you could just read. Oh, and I had the equation. Sorry, it was on the previous one. It's the exact same equation. So you should already have it written once. It's the same thing yet. So what I'm doing is I'm going to jump up here. So this was my pressure. This is my volume. This is my temperature. But I want to talk about that number, the R value. The R value is dictated by which variable? Which one do I have to look at to get the R value right? The pressure. On Friday, we are going to give you this one. We'll give you that. Problem is that's not that one. If you can memorize other ones, that's great. Otherwise, you have to figure out how to convert it. So I could convert this to ATM. I would divide that by 760. But, anybody know the number for the R value for this? 62.4. If you have that down, great. If not, we're going to have to figure something out. You got to have a match. If it was KPA, it'd be 8.314. They are important numbers to know. I know I say this a lot and I joke around about it, and I get because you care about it, but you got to care about this. Like people can remember where the super gun is or the special weapon in some desk drawer on the 4th level of some building and like 2 COD games ago that you haven't played for years. Well, if you can remember that, you can make yourself or try to make yourself care enough to try to have these numbers down for this. Please, suggestion. Try this once. This times this, hit divide, and then hit divide. The less you use parentheses, unless you're really confident and you can see it on your calculator, no one feels like they can trust that. It's at 735 times 10, and what I worry about always is when you divide this, then you hit multiply, and you didn't have that in parentheses where this is actually being divided by that. So if you don't believe me, you can hit 735 times 10, you hit divide, 62.4, and then you hit divide again, 294. Why 294? I needed to add 273. Remember that. If you get that, you're going to have a mole of something. So I'm hoping that you try it my way once. Just try it. Multiply, multiply, divide, divide. And I got this. And the reason why I have it written this way is that now I'm here. I just go boom, boom. I finish with a T-chart. And to be honest, you have the exact T-chart already because we're ending the same way. I'm doing the exact same problem just in different conditions. So this is the exact same ratio that you had before. I'm doing the ratio now, and then I'm doing the math. So you can literally just transfer what you just had from the previous problem. Right? So it should be 1. Should be 4, should be 1, should be 18. The only other type of problem that we're going to have is that you could start up here and you could end down here, not at STP. So you'd start with a T-chart and you'd end with an ideal gas law. So you could have all T-charts, ideal gas law to begin with, end with a T-chart, or start with a T-chart, end with an ideal gas law. So this one we started with an ideal gas law. We're We're ending with a T-chart. .8 grams water. So, technically not new, but we wanted to go over it one more time with you because it does take some practice. Hopefully that is looking familiar. You're going to get a little practice on that with your sheet, okay? There's one thing new though, and it's the least complicated process-wise. So in a second, I'll just let anybody finish this up. And we're going to learn that. We'll calculate it out. We'll do a couple problems, and then we're going to talk about fire suppression systems. So, all right. It's called Graham's Law of Diffusion. I know it looks really big, but there's not a lot to it. I'll show you how we do it all. I'll do a demo with you today. Hopefully it works. It's kind of half work today. So you can just kind of write this for now, if you'd like. So it's rate A over rate B, and then it's the square root of molar mass of B over molar mass of A. So, what is a fusion? Reminder, what it is, it's about gases. It's a property gases have. It's the ability to leak out of a small opening or a small hole. So you have the experience, it's like balloons. Balloons go flat. Why? Because the gas slowly seeps out of small, little tiny openings and the air escapes and the balloon gets smaller. Bike tires, other things like that, car tires, all that stuff. So, what I want to ask, you don't have to write this equation, but here's basically my question. Which one will fuse faster, NH3 or HCl? And that's going to be my demo. Putting money down. Well, you can actually predict beforehand. We're not able to say how fast something goes, but I can say how much faster it went. Like, hey, it went twice as fast, or it went half as fast. So, in your experiences, I'm not dropping something. I'm talking about sheer speed. Big things, heavy things, or light things? Which ones are faster, usually? Like semi, sports car, Covey, Shack, right? Usually, things that are lighter, that are smaller, usually are faster. Then I said elephant and mosquito, and we actually had a long debate, and I'm like, that one might have been a really bad one. I don't know.
Well, because mosquitoes don't have legs. I mean, they do have legs, but they don't use them. They move with their...
I meant it would fly.
They fly.
All right, I'm saying the mosquito flies and the elephant runs. I didn't mean like both with their legs.
Oh. Okay, but like...
Because then I'd be like lion and shark, and then you'd be like, wait a minute, what? Lions can't swim as fast as sharks. Like, of course I wouldn't. Okay, this is how we do this. So just write NH3 versus HCl. This is how we're going to set this up. Oh, actually, sorry, I already have part of it. I'm just writing over myself here. What we do, there we go. Which one's lighter? So you got to look at the periodic table. Which one's lighter? It's not too, once you look at it, it's pretty quick. You can find it pretty quickly. NH3 or HCl is lighter? NH3? Yeah, that's lighter. So I'm going to say that's faster. If you're asking which one is faster, which I am doing right now, I didn't write that on there, but I'll do this, faster. There. Oh, now I'm asking. Then it's rate of NH3 versus rate of HCl. There's no math here. I'm just saying it's the rate versus the rate. It's comparison. Please stay with me.
Comparison.
Like a ratio. We're comparing them. But what's the only trick that you're kind of noticing is that I have rate of A over rate of B. What happens there? They flip. So I got to put the masses opposite. So NH3, N is 14, H's are 1. So 14 plus 1 plus 1 plus 1. That's 17. HCl, Cl is 35.5 plus 1 is 36.5. That's it. Just calculate it. So do it first, then take the square root. So 36.5 divided by 17, then take the square root of that. And what I get, and you should try it, so you're seeing if you're getting these numbers correctly. I want to talk about what that number means. It's important to understand it. So if you don't get that, maybe you didn't take the square root. This is what it means. It means that if you had two balloons, and you had a balloon of NH3 and a balloon of HCl, which balloon would be bigger? It's the one that wouldn't fuse as fast, meaning it wouldn't leak out as quickly. So actually the HCl one would be larger because NH3 effuses faster. Right? It fuses faster out of the balloon. It effuses basically 1.5 times faster than HCl. So I want to do a demo with this. And it's with some pretty strong stuff. So we'll see how it goes.
No, I don't.
Okay, I'm going to do this a little differently than my other hours. So I am working with pretty strong chemicals here. This is 12 molar HCl, double the strength from our lab we just had that ate away that piece of zinc in seconds, or in about a minute. That's really strong. This is basically ammonia. This is the stuff make a long story short, I was telling this during our lab safety contracts a little bit. I had a really good friend. It was concentrated like this, but a huge bottle in our chemistry class when I was a kid. And my friend asked if he could take a huge whiff of it, because my teacher said that it was really strong, really strong. He's like, oh yeah, how strong? I'm like, I want to smell it. He's like, no, you got to waft it. He's like, no, I bet I can smell it. It's like, teacher, let him do it. Really bad move. So he opens it up. My friend comes over, takes a big whiff, and never stopped. And he completely passed out from it.
Great.
You miss those days? Yeah. We call it the incident. He can't. He burned his nasal passages so bad that he had permanent damage. He can't smell certain kinds of scents, really sweet things. He burned his passages. So it's going to be strong. I got to hold my breath a little bit. What's going to happen is that when these come together, I don't have it up here anymore, it makes a solid, NH4Cl. It's a white solid, and it'll be like a little cloud of smoke. So if I have HCl over here, and I have NH3 over here on the tube, and they come together, where is that cloud going to show up? Is it going to show up in the middle? It's going to show up more towards the NH3, or is it going to show up more towards the HCl? Think about which one effuses faster. So as it's traveling, where is it going to show up? Like over here, towards this way, in the middle, or towards that one? Because the liquid's going to be on each end, and then the vapors come into the middle. Where is it going to end up? So over here, this is 1, middle's 2, over here is 3. 1, 2, or 3. What do you think? 3? Well, I see all the letters. Well, let's find out. He doesn't know what he's doing. All right, so last 2 hours I soaked these. This is what I'm going to try this time. I'm just going to squirt some in, and then I'm going to clog it up. I don't know if it's going to work any better, but kind of have to hold my breath. It's really strong.
That's the ammonia right over
So that's the acid. Hopefully it works. Takes a little while, but trying to let some air move in, but come on. There's nothing to see yet. What's that fairy tale? Emperor's New Clothes, and they trick everybody thinking that he's wearing clothes. Come on, it'll show up.
Nobody looked at the Emperor's New Clothes and it's just like.
Come on. Why aren't you working?
I'm not seeing anything.
Just a sec. Yeah, maybe.
Power of dad.
I'm gonna do more. I'm gonna dab it up. Right, that's a lot. Oh, there's smoke. It worked first. Wow, really well.
Oh yeah, I see the smoke.
Where?
It's almost.
Oh, yeah, up there. I want to hear. Come on. It's funny when things work for you. Like I was walking down the hall after class, and all of a sudden the tube just starts smoking like it was on fire from nothing.
Also supposed to be bad.
Shoot. Okay, well,
We'll see.
I can prove to you there's smoke when I put the two things together. But so this, while I'm hoping it's happening as I'm about to talk, the NH3 diffuses faster, so it should be going faster this way than the HCl going this way. So it should have made the smoke, and you can kind of tell it's a little, a little foggy, but there it is. It's not very exciting, but if I put a black background behind it, you can kind of see it. It's green, I get it.
That's pretty convenient.
You're so mean. So it proves that the NH3 diffuses a lot faster than the HCl. You're like, well, it doesn't smoke all that much. Well, if you put them right next to each other, and you just set them there, it would make a ton.
Take the two bottles and go like this.
Ding, 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 ding. So, anyway. There you go. Woo.
Dab. Nice dab.
All right, so I want to do one more. Again, you don't need to write everything. Just how about, all right, hold on. So chlorine versus carbon dioxide. How would that one look? Okay, so we'll do one more because it's important to talk about this one. So, oops. All right, so first, be really mindful. Hey, it's chemistry. You got chlorine and carbon dioxide gas. It's Cl2. You'll make a mistake on the test. If we just write chlorine, you got to know that they could be a diatomic. So, again, what I want to know is which one's faster. Which diffuses faster. So you could say already, but I want to know by how much. So you could guess by which one does it. Clearly, because one of them's heavier than the other. Which one's the lighter one? So you got to add these up, but then Cl2 would be double that. Cl2 is heavier than CO2. So the lighter one's always the fastest. So if you can plan, if you want to know which one's faster, the lighter one should be on top here because you're comparing it. So it's rate of CO2 versus rate of Cl2. So then what happens? We put the masses. I'm going to just move this up a little bit. So I got to look that up. So Cl2, you got to flip them, is roughly 70.9. CO2 is 12 plus 16 plus 16, 44. Okay? So you divide it, you take the square root. It's going to be a similar number, but again, are you able to do that or not? That's acid burn. Yeah. So we're gonna do a problem in the back here. I'll help you out. We'll have the answer key in the resource room. It's literally the only piece of homework that you have on you after today, so all that. The back is not as big as it looks. I'll talk about that. There's no reason to, guys, just get a piece of paper. So that's what that would be. So much energy for a piece of paper. So that's how that one would work. So let's take a look on the back, number 18. The whole right side of the back goes really fast because all it is putting a couple numbers over each other and taking a square root. But I want to do number 18 on this, okay? I want to talk about how this looks and how this works because it's a little bit of a unique problem. I think it's a harder one, and I think it's important for you to see how it functions. All right, so I'm going to erase this. This was your last one. CO2 effuses 1.27 times faster than Cl2. So let's take a look at 18. Again, the whole right side on the back is just using this. And there's little equations on the top to help you out. What it says that what is the molar mass? Okay, so I got to solve for one of these. If at room temperature, this compound or molecule effuses through a pinhole 2.16 times as rapidly as xenon. So what it's saying is whatever I have effuses 2.16 times faster than Xe. So if I make it equal 2.16, that's where that would go. And I'm doing number 18. And I know the numbers don't make sense on the back, but it's the only number 18 on the back. What do I have here? Okay, if it effuses 2.16 times faster, that means xenon is slower. So xenon would go on the bottom here, and it would go on top there. So I just have to look up what it weighs. That's all I'm doing. So that's 131.3. So because it's Xe, I really don't want to use X. I'm sure math teachers around the world would cringe right now by me putting a question mark, but you can put an X if you want. It's just a little confusing with X and Xe. You can put a Y, I get it. Now you solve. So for some of you, yeah, oh, I know what I'm doing next. If not, this is kind of why I wanted to go over this. This isn't the math. This is the setup. I'm comparing this to that because it has to flip. So how do I get rid of a square root? You square it. So I just want to show you the math on this in case you are having a hard time with it. Now I can use X. So you'd solve for it, and you get a molar mass. But I want to talk about what that molar mass is, because it's a little bit tricky. It's asking for the identity. So last problem that we're doing, really focusing on this, because there's two answers every time, and only one is right. You get 28. You get excited. You feel like you did a good job with the math, and you go to it, and you say silicone. And you write it down, and you're like, why did I get that wrong? These are gases. Gases effuse. So you have two choices. It could be the number that you got. Unfortunately, if you don't know this, the table, all the black is solid, all the blue are liquid, and all the red are gases. I need gas. Another thought. What else could it be? N2? Oh, wait a minute. There are gases that are diatomics. So this is what you do. If it's not a gas, cut it in half once and see what it is. Wait a minute. 28 divided by 2 is 14. Oh, nitrogen. Yes, that's a diatomic. So it's N2. Let me give you an example that wouldn't work like that. Let's say you get an answer of 20.2. You go, 20.2. Oh, that's neon. But that's a noble gas. That's already a gas. If you cut that in half, you're going to have a solid. So it's one or the other. I can't think of an example that gets you two gases either way. So, 70.9. It's close to that. Ga, gallium. Nope, that's not. That's a metal or a metalloid. If I cut it in half, that's chlorine. There aren't that many gases. It's just hydrogen, and then just right here. Okay, so just to summarize that, when you get an answer, is it the pure element, or is it a diatomic? Now, if it was something else like CO2, we'd have to tell you. Like 44. Well, wait, is it carbon dioxide? How was I supposed to know it's carbon dioxide? We'd have to give you some hints, like it's a carbon-oxygen compound, or something like that, and we'd have to give you some extra information. Okay, so that's how that works. So you can take a look, work through it on that back right side. Again, all you're doing is a bunch of just plugging them in. Literally, you're dividing two numbers with a square root. That won't take all that long. So on Friday, this is what the quiz will be basically on. Again, it is a quiz. It is not a full-fledged test. If some people have been hearing today, whoa, Dalton's Law, I don't remember that at all. We've had 2 labs now that we've taken a total pressure and we subtracted like water pressure from it. When you subtract pressures or add pressures together, that's what you're doing. Can you do PV equals nRT? Can you do dirt over P? If it says the word density, that's dirt over P. These 2 we did today. Can you do a T-chart at STP? Can you do one where you might have to start with a ideal gas law and then end with a T-chart? Or
10 minutes later.
or it's a video. I'm just sitting there. You ever do that to somebody? Here, I'm taking a picture and you just take a video of them. Are you taking it? Are you taking it? And then you're like, yes, I did. Thank you. And then, or you could start with a gas law, end with a T-chart, or start with a T-chart and end with a gas law. And then finally, can you just divide 2 molar masses, take the square root, and tell me which one it fuses faster? So, little things from each, and we'll see where we're at, okay? So I'll leave that up for a second while I hand this out. We're going to talk about what we're doing for the next 10 days. Very fun, very different. We're going to not really be sitting and getting lectures. When you get this, you will want to fold it like this. It's like a book. It's like a pamphlet. It should say Chemist on the front when you get it. Fold it. That's how it was designed. You want to? What did you not get one? Start folding. Sorry about that. Now you don't have any. Okay, so fold it up. We got a letter yesterday from a company. It says, Dear Director, our small printing company needs to update our fire extinguisher system immediately to avoid losing our insurance. With our high-tech equipment and computers, a standard water sprinkler system is inappropriate. We understand that buildings with electronic equipment usually have fire suppression systems that use a non-reactive gas. Consider using carbon dioxide gas or a halon 1211 bromochloro-difluoromethane system. The reaction vessel may be located inside or outside the building. Design requirements are enclosed. Due to the fact that we are planning to move soon to a new location, we would like your firm to develop a short-term fix for our current extinguishing needs. We are currently located in Siberia and plan to move to Panama. We understand that our locations could affect planning from one system to the next, but we hope that your firm will be able to make our move as seamless as possible. Sincerely, Greg Lyon. So I got this last night from Greg Lyon, and I thought, you know what, I need to investigate a little bit about what is a fire suppression system. So that's what I did. So I found 2 videos. This one's from NASA. This is a little different than what we are being asked to do. This is, they have a hangar, and they have to fill their hangar up, I don't know where I am on this. They have to fill the floor up in 90 seconds with foam and up to 3 feet in 4 minutes to suppress a flame. So this guy might explain it.
The high foam expansion system. Today's test consists of the foam will mix with the water. It will go through the generators and it will dissipate through the floor. It has to cover under the wing within 60 seconds, about 90%, and then it has to get up to 3 feet of the hanger within 4 minutes.
We are not doing this. This would be really cool. I envision somebody in the back just like, oh, I thought it was Head and Shoulders. What that guy is on fire. That's pretty cool though.
That's crazy. That's how they put on fire. That honestly stopped on fire. Yeah, I did. Whoa! Your mixtape doesn't need fire, Wes.
All right, so that's that one. Now, we're doing more of a gas. This guy has an accent, so you can trust him. He's going to introduce his gas system. This one's not nearly as exciting, but this is what Line Enable's asking. So they have electronic equipment and things that can't get damaged. I mean, obviously, we can all picture if you had electronic equipment and all of a sudden water sprinklers turned on, everything in there is going to be ruined. It's like, oh, we stopped the fire. I don't know if it, besides the building itself, all the equipment is destroyed regardless. I mean, obviously you're saving the building, but you need to save all of the investment that you have.
This environment, so we have desk, running computer, paperwork on the desk and such like, only to prove that the gas will have no adverse effect on the way that the computer works or the equipment within the room itself. We're going to set a fire in a bin on the ground in front of me here, and at the same time we will also have 3 hurricane lamps which will be lit to show you the way that the gas descends in the room and extinguishes the fire.
And then he goes through where it's all coming from. You don't need to hear all of it.
We don't want to cause any charge, and big fenders.
So you'll notice as there's the candles in the corner, the hurricane lamps, they'll slowly go out because the gas slowly comes down.
Straight away you can see that top hurricane lamp has already been extinguished. Just goes to show how effective the gas is. And now the gas is descending, and the middle hurricane lamp has now been extinguished.
The family's safe.
The gas continues to descend, and now we see that the lower hurricane lamp is also extinguished, but the main fire is still continuing. It's fighting the gas. It's quite a fierce blaze, but you can see it's now becoming more sporadic, and as the concentration increases, we get to the point where the flame has now been extinguished. So, we've extinguished the fire, so let's go inside and we'll show you that it's safe for humans, but it's not safe for fire.
He lifted his thumb off of it. All right, so let's talk about your responsibilities with this. Flip the page on the inside, please. We're not going to go through everything today, but we're going to go through as much as you need for now. So, we have been contacted about a very important contract. As part of the job, we will need to build a cardboard 1:100 scale model of the facility. The model should be 30 by 15 by 10 centimeters, according to the plan of the facility shown on the right. We're going to use T-candles, little candles, to simulate fires. You're going to have to do 8 of them in 8 separate rooms. So you have 8 different flames. Okay? All that data you'll have to use for Siberia and Panama. We'll talk about that. And what we need eventually is you're going to have to kind of do a summary about what your plan is, what you're going to think you're going to use, and some of the calculations that you think you're going to have. On the bottom is a tentative timeline. You don't have to be right on that, but it's just kind of like, hey, do we have this done? Do we get this done? Do we have that done? Kind of giving you an idea of where everything is. It's more or less about a 10-day project. So we're going to be doing this in class, like not like, oh, so we're going to be doing this out of class and we're going to be lecturing about other things. No, this is, after this quiz on Friday, this is your class for the next week and a half or so. On the right is the budget. You get $225,000 per group. But everything's expensive. To be in lab, to use the facilities, to use utilities and things like that. Every time we're working in the lab, things is going to cost you $15K a day. Disposal, things cost money to get rid of. Chemicals, chemicals cost money. Everything costs something. But a lot of that stuff you may not need. Use an English term, those are red herrings. They may be needed, may not be needed. If, just look at the one in the middle, it says model building in parentheses cardboard. It costs $30,000 for cardboard. If you bring in your own cardboard, it's free. So if you have a shoebox somewhere, now it's got to be these dimensions, if not we got to cut them down. And I always love my favorite question is, well, mine's only 13.5 centimeters wide, is that okay? No, like if it's not the dimensions of their building, they're not going to care. It's got to be their dimensions. So there are things that you can bring in to save your team, your company money. All right. One suggestion you could start to be ready for next week. You could be bringing in cardboard. You could be bringing in tape, glue guns, bottles like 2 liters or milk jugs or whatever, because you're going to need things like that. Tubing. Just a suggestion. We will have some. You can buy some from us. But if you're feeling like you're going to go over, because there are things called OSHA fines, you're doing things that are not quote unquote safe or breaking certain rules, it's on the right, your company could get dinged for a $10,000 OSHA fine. You don't have that much wiggle room. So, suggestion, you go to places that have tubes on a reel, like Fleet Farm, for example, versus Home Depot. And I'm not trying to sell one or the other, but whenever I go to Home Depot, they're all pre-packaged. And it costs like $4 or $5 for like 8 feet total. Go to Fleet Farm, I get 8 feet, it's like 45 cents because it's not pre-cut. So just a suggestion. And I've had groups sell to other groups. Flip to the back. That's the rubric. We'll talk more about this, how it's graded. We're not going to go through each thing, but at the ending, if you're like, well, we didn't know. We are grading using this exact form. So it's like, did you have it? Did you have it? Did you have it? So it's not like, oh, wait, oh, shoot, we didn't know that. We're using this exact form. And if it's going to change, we would give it to you way ahead of time. Okay, so you're probably thinking, I have no idea what we're actually doing. Here is the challenge in front of you. And I'm going to show you some images. Your challenge is the design. First, you have to make a building. Everybody's building is going to look basically the same. But you have to, you get the, okay, I'm not strong at chemistry. Maybe you're really creative. Maybe you're really good with construction or putting, problem solving and building. And great, then that's going to be your strength. There's always some beautification of the building, making it look official. You can't walk in there and it's a shoebox that says Nike on the side and there's a bottle that says Ice Mountain Water still. Like, you wouldn't bring that to a board of directors. You want to present it looking professional. So, these are some from a long time ago. Here's what you are charged with. You need to have a liquid and a gas. I keep saying that. Liquid and a solid. They need to be mixed, but you have to keep them apart until you want to mix them. So you can't come up on the day that we do this, like I got the solid, got my liquid, pouring it in. That's like presenting the board of directors, I got an idea. You're going to push this button. Out of the woods will come a giant. The giant will come. He will have both chemicals, and he will pour and go, there you go, you're welcome. And then he walks away, and he saves your building. Like, you need to have some sort of mechanism and something. I've had groups actually make it so it's electronic and it mixes. That's really rare. I had a group have their building be lit. They had a battery hooked up to it, and they actually had working lights. I mean, I've had all sorts of stuff. But you have to mix them, and then you have to channel the gas into 8 separate rooms. That's the umbrella of it all. That's what you need. You're keeping a liquid and a solid apart. You mix it when you want to mix it. The faster you mix it, the better it is. The fastest one I ever had was like 1.15 seconds. Like, all the candles were out in just over a second. From when I said go, they turned it, candles went out. And then they channel. You got to beautify it. These are not great examples. I'm not trying to show you the best because then you all will mimic that. These are like 10 years old now. This one, not the greatest. They just pushed this through it. It broke a seal and then the liquid went in. They had a parking lot. Here's another parking lot. This is all sealed, but they sell Lipton green tea. This guy's stealing hubcaps. That guy's on a toilet. They have a subterranean one. Again, they have liquid, solid, subterranean. All the gas went in from the top. Gas came in from the bottom. They had a fossil down there. They got creative. Just because I coach tennis or Mr. Blackford or Mr. Neubauer are involved in basketball or football, doesn't give you extra credit for putting a tennis court or a football field next to a printing company. So just FYI. And then that. So what we are asking you to do is you are going to be in a group with potentially a group of 4 within this large group. Now, someone might not be here right now, and if they're not, you can still put their name. You can request, and it's only requesting your top and your second choice of who you may want to work with. Think about this for a second, though. Now, I want to work with my best friend, or I want to work with someone who I might actually do well on. This isn't really a discussion. You just put your name on there. Then, guys, we don't have a lot of time. So, we will get these groups all decided and we'll email them out. We'll also post them in between the chemistry rooms on the bulletin board. We will usually, how this works, we usually take a pair, like 2 people that we know would work well, and then we take a totally unrelated pair that we know would work well. And the goal sometimes, not always, is we put those 2 pairs together. So if you're thinking I'm going to get into a group with 3 of my other friends, that's pretty rare, only because we have found usually those groups don't work actually all that well together. So start thinking, hey, do I have some cardboard boxes? Do I have bottles? Do I have glue guns? Do I have straws? Do I have tubes? Things like that. You can bring some of those things in. Please don't be foolish and bring like a box cutter into school. We have box cutters.
So you have to put 2.
You don't have to put 2.
Just 1.
The first one you put is your top choice. I don't want friendships ruined. Hey, remember 10 years ago when you put my name at number 2? That's why we're still not friends. Put it face down then, and then you can hand it back down this way. Reminder again, your performance lab is due today. Blackford, you want to hit the... So when you have a name, put it face down and hand it back. It's got to be within this room. If you put someone that's not in this hour, it doesn't do anything. So that's where we're heading.